So this afternoon, we're going to start with a talk by Tom Hartman on 3D gravity.
It's on, oh. Okay, thanks very much. It's great to be here and be able to speak at this exciting workshop. So let me get started. So pure gravity in 2 dimensions, or dilettante gravity, is dual to random matrix theory. And this suggests that pure gravity in 3 dimensions should be dual to a random 2-dimensional conformal field theory. On both sides of this equation need to be defined. On the bulk, pure 3D gravity means, roughly speaking, that the only field is the metric, and that we should define the theory somehow by integrating over metrics on fixed topology and then summing over topologies. This sum is divergent, but can hopefully be regulated to make sense of it. On the CFT side, I think this is probably harder. We need to understand what it means to have a random 2-dimensional conformal field theory. There's a big difference between random matrix theory and random CFT, which is the constraints of locality in the boundary directions. So those constraints are implemented by the bootstrap. And that means that somehow what we're looking for is to understand random solutions to the 2-dimensional bootstrap equations. So there are several approaches to do this, where you construct random data that satisfies the bootstrap constraints, either directly from the bootstrap equations or from something like a tensor model or spectral analysis. But so far, I think all of these proposals, well, there are many things that you can calculate this way, but so far, all of these proposals, I think, are incomplete. Regardless of how it's defined, the observables that we're interested in a random conformal field theory, are the statistics of the CFT data. So the statistics of the spectral density and the OPE coefficients. I'm especially going to focus on the OPE coefficients. So these are the CIJKs, which are the matrix elements of the primary operators O. In this talk, I'll focus on the bulk theory. So I think one of the most interesting questions here is to better understand the boundary theory. But actually, there are many things still to learn in the bulk. And I think by organizing the bulk theory in different ways, we can also learn about the boundary ensemble. So I'm focusing here on the gravity path integral that calculates the statistics of OPE coefficients for heavy operators. That is, operators that are dual to black hole microstates. I'm going to talk about 2 ideas. The first is to formulate a holographic dictionary directly for the OPE statistics of the heavy operators. And this will be a rephrasing of the dictionary that we already know, but I think it's useful because it strips off some of the complexity associated with the asymptotic boundaries. And the statement is that these OPE statistics are calculated by a gravity path integral on a finite region of Euclidean spacetime with fixed area boundary conditions. This part of the talk actually applies in principle to any number of space-time dimensions with a focus on d equals 3. In the other idea that I'll discuss is applying this to 3D gravity. And this, in fact, leads to a new approach to calculate the path integral by decomposing 3 manifolds into tetrahedra. Actually, they're not ordinary tetrahedra. They're what are called generalized tetrahedra. And this is something that the mathematicians will tell us are a useful way of decomposing 3 manifolds with boundaries. And so we'll get into this problem of generalized triangulations, which is a decomposition into these generalized tetrahedra. So before we get to the main ideas, I want to cover a little bit more background on OPE statistics in 3D gravity. The OPE statistics are calculated by space-time wormholes. The leading term is a 2-boundary wormhole called the C0 wormhole. This is a special example, a special case of the Malacena-Maus wormhole studied long ago. So the picture here represents a solution of AdS3 gravity and Euclidean signature with 2 asymptotic boundaries. So this is one copy of the CFT with 3 operators inserted. This is a second copy of the CFT with 3 operators inserted. So by the usual dictionary, this calculates a product of 3-point functions. And with the interpretation that the wormhole is calculating the connected contribution to an ensemble average, this tells us the variance of the ensemble. So you could do this calculation in 3D gravity, and the result is a function that actually was already known from the conformal bootstrap called C0. The details of C0 won't be necessary, but this is something that it's closely related to the geodesic structure constants, and it's a known function of the conformal weights. I'm parameterizing the conformal weights H with the Liouville momenta P, I'll mostly be talking about cases where the operators are above the black hole threshold so that P is a real number. Although in this picture, P is imaginary, because in this picture I've drawn a picture of some conical defect operators, and those correspond to particles that are below the black hole threshold. It's convenient to define normalized OP coefficients with unit variance. So the little c's are the ordinary OP coefficients. The big C's are the OP coefficients with these factors of C0 divided out. Now that's just the leading Gaussian term. There are some other terms that you can calculate by standard metric, using the standard metric formalism. And we calculated some 2-boundary wormholes that way and some very special, highly symmetric multi-boundary wormholes. But that method just does not generalize very easily. And what we'd like to be able to calculate are much more complicated wormholes of with arbitrary numbers of boundaries, various insertions, and complicated topologies. In particular, there are non-Gaussian corrections like the 4-boundary wormhole on this slide. So this is a contribution to the 4th moment of the OP coefficients because it has 4 boundaries. And we didn't know how to find the metric on this geometry or to calculate this amplitude in the metric formalism. We did know how to calculate it thanks to the work of Collier, Eberhard, and Zhang on the Virasoro TQFT. So Virasoro TQFT is a topological theory related to SL2R Chern-Simons theory that provides simple diagrammatic rules to calculate any wormhole amplitude of this type in 3D gravity. So in Virasoro TQFT, and the statement is that gravity is two copies of the Virasoro TQFT. So you take the TQFT amplitudes and you mod square them, and those give you the wormhole amplitudes. So for example, this wormhole that I had on the previous slide, the C0 wormhole, in the language of Virasoro TQFT, this is the theta graph, this one here. So each vertex of the graph represents one of the AdS boundaries. So this is the C squared. And you want to calculate this in the topological theory in the TQFT. I've normalized the vertices and everything in this theory so that this just gives 1. The other one that's important for our story is the non-Gaussianity wormhole. So this is the 4th moment of the OP, a contribution to the 4th moment of the OP coefficients. And this wormhole that we had up here in Virasoro TQFT language becomes this Wilson line network where you contract these, you have a trivalent graph that's contracted in a way that looks like a tetrahedron. The Virasoro TQFT amplitude for this case, for this tetrahedral graph, is the fusion kernel for crossing of the 4-point function in a 2-dimensional CFT. So this fusion kernel, well, up to normalization factors, is the same as what's called the Virasoro 6J symbol. It's some function of 6 conformal weights, 4 for the external operators and 2 for the 2 internal operators. So this is the function that takes a 4-point conformal block on the sphere in one channel and expands it in the other channel. And the Virasoro TQFT approach is very powerful, and it essentially lets you calculate any particular wormhole that you want very easily by following these diagrammatic rules. But it doesn't answer everything. There are still questions about understanding contributions to the path integral from non-hyperbolic topologies, so topologies that don't admit a saddle point to expand around. In that case, the TQFT is not quite the same as gravity. There's even some more pedestrian issues with just interpreting the geometries that come out of this. So the Chern-Simons or TQFT method makes the calculations very easy, but it sort of obscures what geometry you're actually talking about. And it can be difficult to take a calculation like this and try to interpret even ask the question, what is the semi-classical geometry here that we're talking about, becomes a difficult question when you phrase it in this way. In particular, Virasoro TQFT, there's no difference between this TQFT calculation for heavy operators and the TQFT calculation for light operators. Although if you try to formulate this in the metric, it's going to be very different. They have different topologies, they have different boundary conditions, but all of that is being sort of hidden by working the TQFT language. So that's one of the things that I'm going to have more to say about later in the talk. So to get into what I want to talk about today, I'm going to start by discussing gravity on a finite region. When I say finite, I'm talking about we're doing the gravitational path integral. So by finite, I mean compact. So we're doing the path integral on a compact Euclidean spacetime with boundary. And the semi-classical saddles of this path integral will have finite volume. Consider 3D gravity on a compact three-manifold with boundary. Okay, so the boundary is some union of Riemann surfaces. The bulk can be something very complicated with handles and holes and whatnot. And the boundary condition that I want to impose is to fix the lengths or the dihedral angles of geodesics on the boundary, allowing everything else to fluctuate. So you pick a Pants decomposition of each Riemann surface on the boundary, and then you impose a length or an angle at each of those curves. The classical solutions with these boundary conditions, with both cases, either lengths or angles, the boundary is what's called a pleated surface, which is a surface that has planar faces with vanishing extrinsic curvature, which join on edges where it can bend into corners and where there's non-vanishing extrinsic curvature. So it's something like a polyhedron with straight faces. This picture is supposed to show locally what it looks like near one of these blue lines. So you get these corners at the ends of the manifold. On each of these blue lines, we're imposing fixed length or dihedral angle, which is the interior angle that it bends at that corner. These boundary conditions admit a consistent variational principle. You have to add boundary terms to the action depending on whether you want to fix the lengths or the angles, but that you can do. It admits classical solutions sometimes. So rule of thumb is that when things are sufficiently complicated, you can find classical solutions. Meaning, if I just draw a simple handle body, let's say, and I pick curves, I pick the Pants decomposition in a simple way, I probably won't find on-shell solutions. But if I pick a complicated topology or I pick curves on these boundary surfaces that wind around in some complicated way, then that can be enough to support classical solutions. And you can find those solutions explicitly. Now, this idea of imposing boundary conditions of studying AdS with finite boundaries is sort of unfamiliar. Usually we put boundary conditions at infinity. But in many ways, this is actually simpler than the usual story. At infinity, you have to put an infinite amount of data. Whereas with finite boundary conditions in pure gravity, there's a finite amount of data. You're just specifying, in the case of fixed lengths, you're specifying a point in Teichmuller space, which for each genus G component of the boundary is just 6G, 6G minus 6 real numbers. So there's just a finite set of numbers that you have to choose here. The other advantage is that these boundary conditions allow you to directly calculate the OPE statistics, which is what we care about when we're studying the ensemble version of the duality. Roughly speaking, you can think of these compact manifolds in the core as calculating the OPE statistics, and the asymptotic ends that we've stripped off, those are responsible for the factors of C0 that we've normalized by, and for the conformal blocks that give a lot of complicated position dependence in the observables of the CFT. Fixed area boundary conditions, a lot like this, have been considered before, especially in the work of Dong and Maroff and collaborators. The only difference here, these are the same boundary conditions. The only difference here is that we're imposing these boundary conditions on a compact manifold. And the point is that you don't have to, they were thinking about things like fixed area states for black holes where you have asymptotic ends. And here we're just studying compact manifolds. And the point is that you can still find classical saddles. So now let's restate the results of Virasoro TQFT in this language. The statement is simple. It's just that the fixed length, so the gravitational path integral with fixed length boundary conditions, which I'll call ZL, is the Virasoro TQFT amplitude squared. I've normalized things in order to strip off the factors of C0. And so the fixed length gravity path integral is the properly normalized Virasoro TQFT amplitude squared. This is just restating the results of Collier, Eberhard, and Zhang, now in this language of the compact manifold in the middle. The argument for this is very easy. It's just to reattach you have this result for the compact region, and you can reattach this to the asymptotic boundaries and recover the usual statement that relates Virasoro TQFT to the observables of 3D gravity. The fixed length saddles can be constructed explicitly by gluing together generalized hyperbolic tetrahedra. So a generalized hyperbolic tetrahedra is a shape that looks like this. It's a polyhedron with 8 faces that's obtained by taking a tetrahedron in hyperbolic space and chopping off the corners in some prescribed way. And these become the building blocks for the fixed length saddle points that you construct. And you can check that the classical action of these saddle points agrees with the predictions of Virasoro TQFT using some asymptotic formula for the 6J symbol that relates it to the volume of the generalized hyperbolic tetrahedra plus some corrections from corner terms. But it turns out that there's a systematic exact way, so that's a semi-classical statement, but it turns out there's a systematic exact way to understand the decomposition into tetrahedra that goes through fixed angle boundary conditions. So for our purposes, actually fixed angle will be more interesting, and that's where we're going to turn to now. So first, let me summarize the main result, the fixed angle boundary conditions. The claim is that the gravitational path integral on a compact region with fixed angle boundary conditions is a different topological theory called the Conformal Turaev-Viro theory, or CTV. So CTV is a different topological theory that you can think of as sort of a dual formulation of Virasoro TQFT. The derivation of this, or the logic anyway for the derivation, is straightforward. We're going to start from the fixed length result that said that the fixed length path integral was Virasoro TQFT squared. And then we're going to take a modular S transform of both sides of this equation. The modular S transform on the gravity side is actually the same as just the change of boundary condition from fixed length to fixed angle. So what we need to show is that the modular S transform of Virasoro TQFT squared is the Conformal Turaev-Viro theory. And that's what we're going to do in the rest of this talk, is to define carefully what I mean by CTV and then explain how it is that we can take the modular S transform. Okay, so Conformal Turaev-Viro theory. CTV is a topological theory that assigns amplitudes to trivalent graphs like Virasoro TQFT. First, I'll describe it just in the language of TQFT without any reference to gravity, and we'll come back to gravity later. I'll write the partition function this way, where M sub E is a closed 3 manifold, the embedding manifold. Gamma is a trivalent graph with edges labeled by conformal weights P. Now we want to calculate or define how to calculate this partition function. The first step is to choose a triangulation T of the graph gamma embedded in the 3 manifold. The edges of the triangulation that belong to the graph are called the external edges, and all of the other edges are called internal. Now, to each tetrahedron in this triangulation, we assign a Virasoro 6J symbol. If the tetrahedron has edges labeled this way, then this is the 6J symbol that we assign. We've seen the 6J symbol before, but this actually, it's important that the rows have been swapped here. Before it was P1, 2, 3, and 4, 5, 6, and now it's 4, 5, 6, 1, 2, 3. This dualizes the tetrahedron, swapping faces for vertices. Now I can define the amplitude of CTV. So we give the Virasoro 6J symbol for each tetrahedron and take the product of all those. And then we integrate over the conformal weights on all of the internal edges with the Carty density of states, rho 0. That's the definition of the CTV partition function. A few comments and caveats. This is the natural generalization of the standard Turaev-Viro theory, which is well known in the context of rational or compact CFTs. This is a natural generalization to the non-rational case. However, there's an important difference, which is that in CTV, the total number of states is infinite. In the standard Turaev-Viro theory, there's an important role played by the total quantum dimension of the rational CFT that you're talking about. And here, the analogous thing is the integral of the Carty density of states, which is just infinity. So many of the things that are done in ordinary Turaev-Viro theory just don't work in CTV because they involve divergent factors of n. In particular, we have to check that this definition makes sense. In order to make sense, the definition that I gave here, we need to check that the integrals are finite, and we need to check that it's independent of the triangulation. I use the triangulation to define the amplitude, but it needs to be independent of the triangulation that we could choose in many different ways. It turns out that this infinite factor of n has the effect of restricting you to certain types of triangulations. The full set of triangulations can be generated by retriangulating your manifold with Packner moves. In 3 dimensions, there's a 2-3 move that that adds an edge to 2 tetrahedra, turns it into 3. And there's a 1-4 move that adds a vertex in the middle and divides 1 tetrahedron into 4. In this theory, the 2-3 moves are allowed that just add an edge, but the 1-4 Packner moves are not. So you're not allowed to add internal vertices like this to your triangulation. If you do, then you get infinity. So trying to add internal vertices gives you divergences. So let's work out an example. The example, I think the simplest example, the calculation here, is the knotted handcuff graph that looks like this. So this is a trivalent graph that we're going to embed in S3. In terms of, so we're not doing gravity yet, but if we jump ahead mentally for a minute, in terms of gravity, this is a contribution to the 2-point moment of OP coefficients. It's a correction to that C0 wormhole, because there are 2 vertices here that each represent an OP coefficient, and the p's are the conformal weights. This manifold, this graph embedded in S3 can be triangulated with a single tetrahedron. This takes some staring at the picture for a while, but you can convince yourself that this tetrahedron here, if you take the 2 front faces and you glue those together, you take the 2 back faces and glue the back faces together, that gives you this graph embedded in S3. In this example, all of the edges are edges of the triangulation, and there are no internal edges. So the CTV amplitude doesn't involve any integrals. It's just the product of the 6. We just get a 6J symbol for each tetrahedron. It's only 1 tetrahedron, so the answer is simply a single 6J symbol. Now I'm going to turn to the connection between CTV and the Virasoro TQFT. Well, there's a well-known relationship between the standard Turaev-Viro theory and Chern-Simons theory that applies to the compact case that says, for the case of 3-manifold invariants, it says that the Turaev-Viro invariant is the mod squared of the Chern-Simons invariant. So we can anticipate something similar for our case that relates the CTV theory to 2 copies of Virasoro TQFT, or VTQFT mod squared. It turns out that they're related by a modular S transform. So the modular transform comes in because we have Wilson lines in our observables. So there's some extra dependence. And the modular S transform takes you from one theory to the other. So this is a statement. You take your Virasoro TQFT amplitude for some graph, you square it, and you do the S transform. S here is the kernel for the characters on the torus, which turns out to just be a cosine. So this is really just a Fourier transform. So you can think about it either way. I won't go through in detail the proof of this. It uses something called the chainmail formalism, which has been developed in the compact case. The proofs in the compact case don't carry over here because of those divergent factors of n, but everything can be modified and you can get rid of those divergent factors and it carries through. Geometrically, the chainmail formalism, what it's doing, just to give you some intuition for it, is it's replacing a triangulation by this dual complex that you see living in the middle there. It's called the dual spine. Let's just look at an example. So this example is the tetrahedron graph. Remember, this was one of our leading non-Gaussianities in 3D gravity. The tetrahedron graph in Virasoro TQFT is a Virasoro 6J symbol. We're squaring it, so we get this 6J squared. And now we want to go to the CTV picture. So the triangulation of this graph embedded in S3, you can think of as one copy of the, you could do this with two tetrahedra, which you can think of as one tetrahedron that you double across its faces. So these two tetrahedra are glued together, this face to that one, and the front face, all the mirror faces are glued to each other. So again, the CTV amplitude is very easy to calculate because there are no internal edges. So we just get a 6J symbol for each tetrahedron. In this case, we get this 6J symbol squared. Now, these are not equal. They differ by this row swap, or the duality that dualizes the tetrahedron. And so the general identity between Virasoro TQFT and CTV, in this case, becomes a sort of self-duality relation for the 6J symbol squared. It says if we square the 6J symbol and take the Fourier transform, then we get the 6J symbol for the dual tetrahedron. And this is a true identity. We can also derive, just to give you some sense, I want to give you some sense of how the derivation of this identity goes. So I'm just going to give you the derivation. I'm going to sketch the derivation just for this example. The general derivation of the identity relating Virasoro TQFT to CTV is similar. It's a diagrammatic derivation that follows the same steps, but we can see the basic idea here. So the first step for this example is we want to study this Virasoro TQFT graph squared. So first we're going to try to rewrite it. We're going to rewrite it as a single diagram. So we can do that just by this diagram here, which when you evaluate by the rules of Virasoro TQFT, it gives you one 6J symbol for the inner triangle and one 6J symbol for the outer part. Then you perform the Fourier transform. There's a nice identity, a diagrammatic identity for the Wilson lines of Virasoro TQFT that turns, when you take a Fourier transform, it turns this graph into this one with a loop. This produces the following graph. So when you just Fourier transform all 6 weights, you get this thing that's now connected by loops. So this is called the chainmail diagram, and this is where the name chainmail comes from, because this sort of looks like a bunch of chains glued together. And then simplifying this further, I won't go through the details, but simplifying this further gives the CTV amplitude that we got on the previous slide. So this is sort of how the logic goes, is there's a diagrammatic way of doing the Fourier transform that converts one theory into the other. Now let me return to 3D gravity. So CTV and Virasoro TQFT were both defined for a graph, a trivalent graph gamma, embedded in a closed 3-manifold M sub E. first I have to tell you where gravity lives, because it doesn't live on M sub E. The statement is that 3D gravity lives on the complement of the thickened graph. Okay, so let's look at our example. This is the embedding, and we took one of our graphs, in this case, one of the examples we looked at earlier. Then the first thing we want to do is to thicken out the graph, and gravity lives on the complement M. Now, M is a compact manifold with boundary, and will impose the fixed length or fixed angle boundary conditions on the meridians of the graph, which are the loops in red. In this example, you can find the on-shell geometry, and so this is where gravity lives on the complement. In this example, the on-shell geometry on the complement is a single generalized tetrahedron that looks like that. In general, you can find the tetrahedra of the gravity manifold by constructing the chainmail graph. So you can follow this diagrammatic procedure that I gave earlier. You start from Virasoro TQFT. You apply this procedure. That gives you a chainmail graph. And then the chainmail graph is reinterpreted as a Hagar diagram for gravity. Now that I've described where gravity lives, I can restate and now derive the main result for the fixed angle path integral that I stated earlier. We start from the fixed length path integral. Recall that the fixed length path integral is the Virasoro TQFT amplitude squared. This is just the usual statement of gravity, the relationship between gravity and Virasoro TQFT that's been restated on a compact region by stripping off all the conformal blocks and C0s. Now we take the Fourier transform of both sides. On the Virasoro TQFT side, we've learned that taking the Fourier transform or the modular S transform converts this into the conformal Turaev-Viro theory. On the gravity side, the Fourier transform just turns into the change of boundary conditions. And therefore, we find that the fixed length path integral for gravity is exactly the CTV amplitude. So this is the main result that I wanted to describe. And now I'm going to wrap up with a couple of comments. So now we can calculate the exact gravity path integral by gluing together these generalized tetrahedra. I forgot to mention one thing, which is how they became generalized tetrahedra as opposed to ordinary tetrahedra. So in the Turaev-Viro theory, we have ordinary tetrahedra, but then when you fatten out the graph, that truncates the tetrahedra. So that's how they become generalized truncated tetrahedra. In the semi-classical limit, the CTV result manifestly agrees with the metric formalism. So this was not the case in Virasoro TQFT. It's very non-trivial to check or understand how that agrees with the metric. In this case, it's totally obvious because the asymptotics of the 6J symbol give you the on-shell gravity action for the generalized tetrahedron. And therefore, you can just take your product of 6J symbols in the CTV theory and literally interpret them one for one with the on-shell actions of the generalized tetrahedra that make up your 3-manifold. It also means that we can translate calculations in Virasoro TQFT into geometry and understand, for example, what are all the classical saddle points that correspond to the calculations that have been done in Virasoro TQFT. To do that, you have to construct triangulations. Actually, there's really nice software that the mathematicians have written for this. It's called Orb, where you can just use the mouse to draw your graph, the trivalent graph that you want, and it'll hand you the triangulations, and then you can use that to find your classical gravity saddles. I want to make a few preliminary comments on de Sitter space. So there does seem to be something similar in de Sitter with positive cosmological constant. Actually, the history here is that de Sitter was sort of done first. Actually, this decomposition of gravity into tetrahedra goes back to the model of Ponzano and Regge, who discretized flat spacetime into the 6J symbols of SU2. Then Turaev and Viro introduced this model that uses not the ordinary 6J symbols of SU2, but a quantum group analog of that for the quantum group for SU2. And it was quickly realized that this Turaev-Viro theory could also be interpreted in some semi-classical limit as calculating for you observables in three-dimensional de Sitter. So this has been studied for many years in the spin network community, and seems to be very similar to the identities that I've described here for the AdS case. The difference in the AdS case, it's still Turaev-Viro, but it's a different set of representations for the quantum group. There's one difference in perspective here, which is that I think in the spin network literature, they really had in mind that they were forming a, almost done. They really had in mind that they were forming this fine-grained Planck scale discretization of the manifold. And here, that's not what I'm doing. I'm just decomposing it on extremal surfaces into nice big tetrahedra that you then glue together. In principle, the fixed area path integral that I described on a compact region also calculates black hole statistics in higher dimensions. But I'll just leave it at that and say that if we can find the saddles, then that would be a great way to understand those statistics. There's some hints in the bootstrap literature for what those statistics might look like, but it seems very hard to do exactly. We may have to take some approximations or study various limits to be able to do that in higher dimensions. There are many other questions that are open, but let me not go through them, and I'll just end here. Thank you.
Is there a worldsheet analog of these results in the way that the Virasoro minimal string was related to computations in Virasoro TQFT?
I don't know of one. In principle, we should be able to take the Fourier transform of that and see what it gives. But no, I haven't thought about that.
You started for motivation with that particular four-wormhole geometry. And you said at the time, oh, we didn't know the metric or how to calculate it. And it sounds like, if I understood what you said before, that now you know the metric. Like, not only do you know the amplitude, you actually have a metric.
Yes.
So is this like, are there new classes of exact solutions to Einstein's equations that we know now?
Well, yes. Although they're... Sorry, let me find the right picture. Okay, so this is a hyperbolic tetrahedron. This is a solution of Einstein's equations, but it has boundaries. The new solutions that you find are many copies of these tetrahedra glued together in various ways. Now, there's a large class of manifolds, possibly all of the hyperbolic manifolds that we're interested in, which can be triangulated in this way. So I think the advantage here is you don't have to find a bunch of new metrics. You just take this one, which we know how to construct very explicitly, and we can write down everything about it by going to embedding space, and then we just have to give gluing rules for how the different tetrahedra are glued together.
Okay, and is there like a nice way to extend it to like the more like, more smooth coordinate patches or whatever, like,
global coordinates? Boy. In principle, I think you can do that because you can find the representations of SL2C. So all of the solutions of 3D gravity are quotients of H3 by isometries. And in principle, you can probably use these triangulations to find the group that you're supposed to quotient by, but I haven't actually thought about how to do that in detail. I would say we probably don't even, for the most part, we don't want to do it that way. I think that was how we tried to do it for a long time, was to like find the right manifold. But actually just thinking about it all in terms of triangulations seems to be much easier.
Yeah. So how it feels satisfying to have the manifold. Yeah.
We really do have it. I mean, we have the metric for this. It's just that we have two different coordinate patches and then we glue them together. Or more than two, depending how many.
Thanks, Tom. So I was just wondering, like in the de Sitter case, if you go
Sorry, what case?
in the de Sitter case, if you go one slide back, then so why are you doing like SU2 and not SU2C?
That is a very good question. And so I think, well, that's not what I'm doing. This is what Turaev-Viro did and what the spin network people have been doing for decades. But actually, if you want to make this look more like what I was doing in AdS3, that might be the wrong group to use. And I think this recent work of Gaiotto and Teschner and Hartman may be a more direct route to doing a similar thing in de Sitter. And that's more like SL2C as opposed to SU2.
Viro theory is like defined more on SU.
It's defined, say?
It's more like established for SU2. So, but
You know, the standard Turaev-Viro theory has mostly been studied for the SU2 case, or what's the related to Chern-Simons.
In the past, in like your work and collaborators' work, the way that we would relate like real value of momenta, the local momenta to imaginary values, is we think of like some fixed length boundary and some codeficit angle. Here you're saying that those things are sort of like Fourier conjugate to each other. So I guess, can you help me understand, like, should I think of these things as like an analytic continuation, or should I think of them as conjugate variables?
Well, I think that the angle you have in mind is a different angle. So the length is something that lives on the two manifold, and that's the same length that you're thinking of. That's always the length in Liouville. But the angle is something that lives in the three manifold, because in fact, the intrinsic geometry of the two manifold doesn't even know about the angle. It's just purely hyperbolic, and this is just how it's bent into the three manifold. So it's a different type of angle, and it is conjugate to the length.
In the 2D case, if you consider finite geometry, the geometry typically is a fractal. So in the three-dimensional case, is it also a fractal, or are you thinking about it's actually a smooth finite geometry at quantum mechanics level?
I'm not sure what you mean by okay.
New world, disk.
Everything I'm doing here is expanding around this classical saddle. I should have emphasized that, but this connection between CTV and gravity at this point so far only works on manifolds that admit a saddle point to expand around. So then I don't think there's any issue unless you're talking about something else.
It's exact partition functions of this finite geometry.
On that fixed topology, which we expand around, it's on a fixed topology, but then there's a classical saddle, which is nice and smooth, and that's the one that I've drawn pictures of, and we're expanding around. There are much more complicated three manifolds than the ones that I've drawn here. These are the ones that really gave Thurston and the mathematicians the most amount of difficulty, where the ends become arbitrarily complicated as you go off towards infinity. I have not considered that type. That's a more general type of boundary condition, where, for example, I always chose a Pants decomposition, but you can choose a boundary condition which is imposed on curves that loop around in infinite number of times. And that's what Thurston does.
Yeah, so it should be easy to include world lines in the geometry with your formalism. But what can you say a few words about what it would take to go to Lorentzian signature? But for example, if you want to compute something like an OTOC, could your formalism be used?
I think the answer is yes, but I haven't really thought about it. There was a paper last week by mathematicians talking about some regime where the asymptotics of the 6J symbol give Lorentzian tetrahedra. So that looked really interesting, but I haven't really had a chance to absorb it yet. I think that, yeah, I think there should be a similar story, but I don't really have anything useful to say.
All right, let's thank Tom again.